Wireless energy transmission promises a revolutionary future. But how much of what we hear is actually true? Maxwell's technology claims to deliver power without wires. Yet skepticism remains widespread. This investigation separates fact from fiction. First, let's define wireless energy transfer. It's the transmission of electrical power without physical connections. Nikola Tesla pioneered early experiments in the 19th century. Modern iterations rely on electromagnetic fields. Maxwell's approach uses resonant inductive coupling. This method enables mid-range power transfer. But can it truly replace wired electricity? The short answer, not yet. Wireless charging already exists for small devices. Smartphones and electric toothbrushes use inductive charging. Scaling this up presents major challenges. Energy loss increases with distance. Efficiency drops significantly over just a few meters. Maxwell claims to have overcome this limitation. Their demonstrations show impressive results. But independent verification remains limited. Physics imposes hard constraints on wireless power. The inverse square law governs field strength dissipation. Higher frequencies allow better directionality, but they also raise safety concerns. RF radiation at high power requires careful shielding. Thermal effects can damage nearby objects. Regulatory hurdles further complicate deployment. FCC regulations restrict power levels for consumer safety. Industrial applications face fewer restrictions. Medical implants already use wireless power effectively. Pacemakers and hearing aids benefit from this technology. Electric vehicles may adopt wireless charging roads. Dynamic charging could eliminate range anxiety. But infrastructure costs remain prohibitive. Consumer electronics will likely adopt wireless power first. Laptops and tablets could soon ditch charging ports. Kitchen appliances might get powered countertops. Smart home devices could charge automatically. The environmental impact deserves consideration. Wireless systems currently waste more energy than wired. Efficiency improvements could change this equation. Renewable energy integration presents new opportunities. Solar satellites could beam power wirelessly to Earth. This concept has been studied for decades. Technical and economic barriers persist. Space-based solutions remain speculative. Ground-based wireless grids seem more plausible. Urban environments create interference challenges. Building materials absorb and scatter electromagnetic waves. Metallic structures particularly disrupt transmission. Reliability issues plague current prototypes. Consistent power delivery remains unproven at scale. Weather conditions affect outdoor performance. Rain and humidity alter wave propagation. Security risks accompany wireless networks. Energy theft becomes theoretically possible. Signal jamming could disrupt critical systems. Encryption standards for power don't yet exist. Health concerns understandably worry consumers. Long-term RF exposure effects require more study. Existing safety standards may need updating. Pacemaker interference remains a valid concern. Pregnant women and children might need special precautions. The economic landscape looks uncertain. Infrastructure retrofitting costs could be enormous. Consumer adoption depends on clear benefits. Compatibility standards must emerge industry-wide. The chicken and egg problem stalls progress. Manufacturers won't adopt without devices. Device makers won't include without infrastructure. Government incentives could break this deadlock. Military applications may drive initial development. Battlefield power distribution offers strategic advantages. Drones could recharge mid-flight wirelessly. Forward bases might receive remote power. Emergency response scenarios show promise. Disaster zones often lack functioning grids. Temporary wireless power could save lives. Medical equipment could operate continuously. Communication devices would remain charged. The technology's maturity remains questionable. Peer-reviewed research on Maxwell's claims is scarce. Independent testing hasn't validated all assertions. Some demonstrations appear carefully staged. Measurement techniques sometimes lack transparency. The scientific community remains divided. Some physicists call the claims exaggerated. Others see genuine potential with caveats. Investor enthusiasm sometimes outpaces reality. Stock prices for related companies fluctuate wildly. Media coverage tends toward sensationalism. Balanced reporting is unfortunately rare. Consumers deserve clear, factual information. Hype helps nobody in the long term. Realistic expectations prevent disappointment. Progress happens through honest assessment. Now let's examine specific claims. Maxwell promises whole-home wireless power. This would require enormous energy densities. Safety standards currently prohibit such levels. Room-scale charging seems more plausible. Device-specific targeting appears feasible. Smart beamforming could improve efficiency. But this increases system complexity. Costs would rise accordingly. Another claim involves long-distance transmission. Kilometer-range power beaming defies physics. Atmospheric absorption defeats most attempts. Laser-based systems face even greater hurdles. Thermal blooming distorts high-power beams. Aircraft and wildlife create safety hazards. Ground stations would need precise alignment. Moving receivers complicate matters further. The efficiency equation looks problematic. Wired grids achieve over 95% efficiency. Current wireless systems struggle to reach 50%. Every percentage point matters at scale. Wasted energy has environmental consequences. Renewable sources can offset some losses. But generation capacity isn't unlimited. Energy storage could help smooth demand. Bridges gaps in intermittent transmission. Adds another layer of complexity. Increases overall system costs. The maintenance picture remains unclear. Wireless components degrade over time. Moisture ingress threatens outdoor units. Vandalism could disrupt public systems. Repairs might require specialized technicians. Diagnosing faults presents new challenges. The cybersecurity angle warrants attention. Power networks are critical infrastructure. Wireless links create new attack vectors. Hackers could potentially drain batteries. Denial of service attacks become possible. Encrypted power transfer seems oxymoronic. Signal authentication methods are immature. The regulatory landscape isn't ready. Spectrum allocation is already crowded. Interference with communications must be prevented. International standards don't yet exist. Municipal approvals could slow deployment. Zoning laws weren't written for this technology. Public perception will make or break adoption. Consumers fear what they don't understand. Misinformation spreads faster than facts. The nuclear power industry offers cautionary lessons. Transparency builds essential trust. Independent verification matters most. Academic involvement would increase credibility. Peer-reviewed papers carry more weight. University research could validate claims. National labs might conduct impartial testing. The investment landscape looks volatile. Hype cycles distort rational analysis. Early investors often get burned. Sustainable growth requires patience. Real innovation withstands scrutiny. The engineering challenges are formidable, but not necessarily insurmountable. Incremental progress appears achievable. Niche applications may lead the way. Medical technology shows the path forward. Industrial settings offer controlled environments. Specialized military uses can fund development. Consumer products will follow eventually. The road ahead requires measured steps. Extravagant promises help nobody. Honest assessment serves progress best. Real problems need real solutions. Wireless energy isn't a panacea, but it could transform specific applications. The truth lies between hype and dismissal. Understanding the limitations is crucial. Recognizing the potential is equally important. This balanced view serves everyone best. Now let's examine the physics more deeply. Maxwell's equations govern electromagnetism. They describe how fields propagate. Energy transfer requires careful tuning. Resonance enhances efficiency, but can't overcome fundamental limits. The inverse square law still applies. Field strength diminishes rapidly. Higher frequencies allow focusing, but penetrate materials poorly. Lower frequencies spread widely, making efficient transfer difficult. This is the core challenge. No technology can bypass physics. Only work within its rules. Clever engineering finds optimizations. But no magic bullets exist. Materials science offers some hope. Metamaterials can shape fields. Superconductors reduce losses, but require extreme cooling. Room temperature variants remain elusive. Cost-effective solutions don't yet exist. The efficiency ceiling seems firm. Thermodynamics sets hard limits. Entropy can't be defeated. Some energy will always dissipate. The question is how much. Current systems lose too much. Future improvements may help, but expectations should be realistic. Breakthroughs happen unpredictably, but can't be assumed in planning. The business case must stand today, not on speculative futures. This separates science from fiction. Real engineering from wishful thinking. The market will ultimately decide. Useful applications will thrive. Impractical ones will fade. The technology will find its level. Not all claims will prove true, but some may surprise skeptics. Time and testing will tell. Independent verification is key. Reproducible results matter most. Science advances through evidence, not through press releases. The path forward is clear. Test, validate, then deploy. Skip any step at peril. The stakes are too high. Energy infrastructure affects everyone. Getting it wrong has consequences. Getting it right brings benefits. This balanced approach serves all. Now let's consider alternatives. Wired solutions keep improving. Superconducting cables advance. High voltage DC gains ground. Smart grids optimize distribution. Efficiency reaches new highs. Reliability sets records. Safety improves constantly. Costs continue falling. The incumbent technology isn't standing still. Wireless must compete on merit, not just on novelty. The comparison should be fair. Each has strengths and weaknesses. The future likely holds both. Not either or but and. The right tool for each job. Portable devices favor wireless. Fixed installations may stay wired. Medical implants need wireless. Data centers probably won't. Context determines suitability. Dogma serves no one. Pragmatism guides progress. The energy landscape is changing. Decentralization gains momentum. Microgrids proliferate. Renewables dominate growth. Storage breakthroughs accelerate. Demand patterns shift. Wireless could complement these trends, or compete against them. The interplay deserves study. System thinking is essential. Isolated analysis misleads. The whole picture matters. Energy interacts with everything. Economics, policy, technology. All intertwine deeply. Simple narratives deceive. Reality remains complex. Our understanding must match. Now let's summarize clearly. Wireless energy has potential, but faces real limitations. Maxwell's claims need verification. Some aspects appear promising. Others seem exaggerated. Physics sets firm boundaries. Engineering works within them. Progress happens incrementally, not through revolutions. The future remains open, but must be grounded in evidence, not hype. In reality, not fantasy. This measured view serves best. Now what comes next? Testing, always testing. Validation through repetition. Peer review and scrutiny. Then cautious deployment, followed by monitoring and continuous improvement. This is how real progress works. Not through viral claims, but through hard work. The scientific method endures. Because it works. Wireless energy deserves fair assessment. No more, no less. The truth will emerge, as it always does. With patience and rigor, we'll understand what's possible, and what's not. Until then, healthy skepticism helps, as does open-minded inquiry. The balance moves us forward. Section 2, the road ahead. The wireless energy field stands at a crossroads. Credible research must separate from speculation. Independent laboratories should replicate results. Measurement methodologies require standardization. Efficiency calculations need universal metrics. Safety testing protocols must be established. The academic community should engage deeply. Physics departments could verify principles. Engineering schools might test implementations. Materials scientists should examine components. Peer-reviewed journals must publish findings. Conference debates would clarify positions. The scientific method will settle claims. Reproducibility remains the gold standard. Corporate transparency would build trust. Open demonstrations invite scrutiny. Detailed white papers aid analysis. Patent filings reveal technical approaches. Investors should demand evidence. Due diligence prevents hype cycles. Rational capital allocation drives progress. Media has a responsibility too. Balanced reporting informs the public. Sensationalism serves nobody. Contextualized coverage helps understanding. The engineering challenges demand attention. Thermal management requires innovation. Efficient rectennas need development. Beam steering accuracy must improve. Adaptive impedance matching helps. Smart surfaces could enhance transmission. AI optimization may boost performance. The materials pipeline looks promising. Metamaterials enable novel behaviors. Hypermittivity dielectrics help. Low-loss conductors reduce waste. Advanced semiconductors drive control systems. Manufacturing processes must scale. The regulatory framework needs development. Spectrum allocation requires coordination. Safety standards must evolve. International cooperation helps. Municipal guidelines should form. Licensing procedures need definition. The business ecosystem must mature. Use cases should drive development. Medical devices lead naturally. Industrial sensors follow. Consumer electronics come next. Infrastructure applications wait. The investment thesis requires focus. Niche markets provide revenue. Then expansion becomes possible. The workforce needs preparation. New skills must be taught. Engineering curricula should adapt. Technician training programs help. Interdisciplinary knowledge becomes valuable. The public dialogue needs nuance. Extreme positions hinder progress. Balanced understanding enables decisions. Education materials should be accurate. Museum exhibits could demonstrate. Documentaries might explain clearly. The environmental impact matters. Life cycle analysis is essential. Recycling protocols must exist. Energy inputs should be renewable. Comparative studies inform choices. The geopolitical dimension emerges. Energy independence has value. Resilient grids provide security. Distributed systems resist disruption. Technology leadership brings advantages. The ethical considerations are many. Equitable access deserves attention. The digital divide shouldn't widen. Affordability remains crucial. Safety must never be compromised. The long-term view matters most. Sustainable solutions endure. Short-term thinking fails. Patience rewards the diligent. The future remains unwritten. Our choices will shape it. Wisdom suggests prudence. Vision requires realism. Progress needs both. Wireless energy may find its place. Not everywhere but somewhere. Not solving everything but something. That's how technology evolves. Through careful steps. Not giant leaps. The journey continues. With eyes open. And minds clear. That's the path forward. For Maxwell's claims. For wireless energy. For all technology. Truth withstands scrutiny. Time reveals all. We must simply watch. And learn. And test. Then we'll know. What's real. And what's not. That's how science works. That's how progress happens. Patiently. Rigorously. Honestly. The rest will follow. This response is AI generated for reference only. Please expand. The dream of wireless electricity has captivated inventors for over a century. Nikola Tesla's early experiments with Wardenclyffe Tower promised global energy transmission. Modern companies like Maxwell Technologies now claim revolutionary wireless power solutions. But how much of their marketing matches scientific reality? This investigation dives deep into the physics, economics, and practical limitations of wireless energy transfer. The fundamental principle relies on electromagnetic field coupling. Energy transmits through carefully tuned magnetic resonance. Receivers convert these oscillating fields back into usable electricity. At close range, this technology already powers devices like smartphones. Qi wireless charging pads demonstrate basic inductive coupling. Maxwell's claims extend far beyond these simple applications. They propose room-scale wireless power delivery, even building-to-building energy transfer. Such ambitions immediately raise scientific eyebrows. The inverse square law governs all electromagnetic radiation. Field strength diminishes exponentially with distance. Doubling the transmission distance quarters the received power. This presents an unavoidable physics challenge. Maxwell's proposed solution involves resonant repeaters. Strategically placed coils could theoretically extend range. Each repeater would capture and retransmit the energy wave. But every transfer step introduces significant losses. Current prototypes reportedly achieve 60% efficiency at 5 meters. This sounds impressive until compared to wired alternatives. Copper cables maintain 98% efficiency over kilometers. The wasted 40% becomes problematic at scale. For a 100-watt device, that's 40 watts lost as heat. Multiply this across an entire building's power needs. The thermal implications become concerning. Safety standards strictly limit human RF exposure. FCC regulations cap radiated power at 1 W/kg/SAR. Medical implants require even stricter thresholds. Pacemakers must avoid electromagnetic interference. Maxwell claims their system operates within these limits. Independent verification remains unpublished. Their demonstration videos show careful setups. Controlled environments with optimal conditions. Real-world implementation would face complications. Building materials absorb electromagnetic energy differently. Concrete attenuates signals substantially. Metal structures cause unpredictable reflections. Human bodies absorb 2.4 GHz radiation efficiently. This frequency heats water molecules, our primary component. Thermal imaging of their tests would be revealing. The economic analysis raises more questions. Infrastructure costs would be enormous. Every room needs precisely tuned transmitters. Maintenance requires specialized technicians. Energy theft becomes theoretically possible. Neighbors could potentially siphon power. Encrypted power transfer remains unproven. Cybersecurity vulnerabilities multiply. Hackers might manipulate power delivery. Denial of service attacks could black out buildings. The regulatory landscape isn't prepared. No standards exist for wireless energy grids. Spectrum allocation conflicts with existing services. Wi-Fi and cellular networks occupy similar frequencies. Interference mitigation would be complex. The environmental impact deserves scrutiny. Increased energy waste contradicts sustainability goals. More generation required for equivalent usage. Renewable sources could offset this. But capacity limitations remain. Comparative life cycle assessments are lacking. Manufacturing transmitters has its own footprint. Rare earth metals enable efficient coils. Mining these carries ecological consequences. Recycling infrastructure doesn't yet exist. The medical community expresses concerns. Long-term RF exposure studies are incomplete. Children's developing tissues may be vulnerable. Electromagnetic hypersensitivity remains debated. Precautionary principles suggest restraint. Alternative technologies continue advancing. Superconducting cables achieve near-perfect efficiency. Smart grids optimize conventional distribution. Battery storage compensates intermittency. The business case appears shaky. Why replace 98% efficient wired systems? Niche applications show more promise. Medical implants benefit unquestionably. Industrial sensors in hazardous locations. Electric vehicle charging while driving. These targeted uses make engineering sense. Consumer electronics represent a middle ground. Laptops freeing from charging cables. Kitchen appliances with hidden power. Smart home devices maintaining constant charge. The military pursues strategic advantages. Battlefield energy distribution. Drone mid-air recharging. Forward operating base power. These applications justify higher costs. Disaster response scenarios hold merit. Emergency power after earthquakes. Temporary hospitals and crises. Communication equipment during outages. The scientific method demands verification. Extraordinary claims require extraordinary evidence. Peer-reviewed publications are essential. University replication studies necessary. National lab validation crucial. The investment landscape looks volatile. Hype cycles distort rational analysis. Early-stage companies make bold claims. Market corrections inevitably follow. Sustainable progress requires patience. Real innovation withstands scrutiny. The engineering challenges are immense. Thermal management at scale. Interference mitigation techniques. Adaptive impedance matching. Dynamic load balancing. Precision beam steering. Materials science pushes boundaries. Metamaterials enable novel behaviors. High-temperature superconductors. Low-loss dielectrics. Advanced semiconductors. The workforce needs development. New engineering specialties. Installation technician training. Maintenance protocols. Safety certification programs. The regulatory framework lags. Spectrum allocation policies. Exposure limit guidelines. Municipal zoning codes. International standards. The public discourse needs nuance. Balanced media coverage. Science communication. Museum exhibits. Educational programs. The environmental equation must balance. Life cycle assessments. Recycling infrastructure. Renewable integration. Comparative analysis. The geopolitical implications matter. Energy independence. Grid resilience. Technology leadership. Economic competitiveness. The ethical considerations are profound. Equitable access. Affordability. Safety. Privacy. The long-term perspective is essential. Sustainable solutions. Measured deployment. Continuous improvement. The future remains unwritten. Wireless energy may find its place, not as a panacea, but as a complementary solution, where it makes technical sense, where economics justify, where safety ensures. That's how technology evolves. Through careful steps, not reckless leaps. The truth will emerge. Through testing, through debate, through time. That's how science works. That's how progress happens. Section 2, The Road Ahead. The coming decade will determine wireless energy's fate. Several critical developments must occur. Scientific validation stands paramount. Independent laboratories must replicate results. Measurement methodologies require standardization. Efficiency calculations need universal metrics. Safety testing protocols must be established. The academic community should engage fully. Physics departments could verify principles. Engineering schools might test implementations. Materials scientists should examine components. Peer-reviewed journals must publish findings. Conference debates would clarify positions. Corporate transparency would build trust. Open demonstrations invite scrutiny. Detailed white papers aid analysis. Patent filings reveal technical approaches. Investors should demand evidence. Due diligence prevents hype cycles. Rational capital allocation drives progress. Media has a responsibility too. Balanced reporting informs the public. Sensationalism serves nobody. Contextualized coverage helps understanding. The engineering challenges demand attention. Thermal management requires innovation. Efficient rectennas need development. Beam steering accuracy must improve. Adaptive impedance matching helps. Smart surfaces could enhance transmission. AI optimization may boost performance. The materials pipeline looks promising. Metamaterials enable novel behaviors. Hypermittivity dielectrics help. Low-loss conductors reduce waste. Advanced semiconductors drive control systems. Manufacturing processes must scale. The regulatory framework needs development. Spectrum allocation requires coordination. Safety standards must evolve. International cooperation helps. Municipal guidelines should form. Licensing procedures need definition. The business ecosystem must mature. Use cases should drive development. Medical devices lead naturally. Industrial sensors follow. Consumer electronics come next. Infrastructure applications wait. The investment thesis requires focus. Niche markets provide revenue. Then expansion becomes possible. The workforce needs preparation. New skills must be taught. Engineering curricula should adapt. Technician training programs help. Interdisciplinary knowledge becomes valuable. The public dialogue needs nuance. Extreme positions hinder progress. Balanced understanding enables decisions. Education materials should be accurate. Museum exhibits could demonstrate. Documentaries might explain clearly. The environmental impact matters. Life cycle analysis is essential. Recycling protocols must exist. Energy inputs should be renewable. Comparative studies inform choices. The geopolitical dimension emerges. Energy independence has value. Resilient grids provide security. Distributed systems resist disruption. Technology leadership brings advantages. The ethical considerations are many. Equitable access deserves attention. The digital divide shouldn't widen. Affordability remains crucial. Safety must never be compromised. The long-term view matters most. Sustainable solutions endure. Short-term thinking fails. Patience rewards the diligent. The future remains unwritten. Our choices will shape it. Wisdom suggests prudence. Vision requires realism. Progress needs both. Wireless energy may find its place. Not everywhere but somewhere. Not solving everything but something. That's how technology evolves. Through careful steps. Not giant leaps. The journey continues. With eyes open. And minds clear. That's the path forward. For Maxwell's claims. For wireless energy. For all technology. Truth withstands scrutiny. Time reveals all. We must simply watch. And learn. And test. Then we'll know. What's real. And what's not. That's how science works. That's how progress happens. Patiently. Rigorously. Honestly. The rest will follow.